This video is an introduction to functions. A relation is a set of pairs of input and output values. It can be expressed as a set of ordered pairs, as a mapping, a table of values, or as a graph. So here's an example. So here we have the relation expressed as a set of ordered pairs. This is a mapping. It's kind of like you have this bubble here, which is your input values, this bubble over here, which is your output values, and each input is mapped to an output, or each input can be mapped to two different outputs. Table of values, x's and y's, you're probably familiar with, and then a graph where you plot the points on the coordinate plane. The domain of a relation is the set of all of the inputs, or the x-coordinates of the ordered pairs. The range is the set of all outputs, or the y-coordinates of the ordered pairs. For example, in the relation above, the domain is -3, 3, and 4, and the range is -1, 3, and 4. Now, a special type of relation is a function, and that's a relation in which each element of the domain corresponds with exactly one element of the range. Each x is mapped to only one y. So let's take a look at a couple examples here, and we need to determine whether each of these is a function. So here we have a set of ordered pairs, 0, 0, 2, 4, -2, 4, 3, 9, and -3, 9. So is this a function? In other words, is each x mapped to or paired up with only one y? Well, here 0 only goes to 0. I don't see any other repeated zeros as my x-coordinates. I only have 1, 2. I only have 1, -2, 1, 3, and 1, -3. So yes, this would be considered a function because each x is paired up with only one y. Let's take a look at number 2 here. Here we have a mapping. We have our domain bubble and our range bubble. And this one is not going to be a function because this value 10 is actually mapped to -2 and to 4. So no. In other words, we would have the ordered pair 10, -2 and the ordered pair 10, 4, and you cannot have a repeated x in order for it to be a function. If the relation is expressed as a graph, that is, on the coordinate plane, you can use the vertical line test to determine whether or not it is a function. The vertical line test says that if a vertical line intersects the graph of a relation in more than one point at a time, then it is not a function. So let's take a look at these two examples here. So A here. So you need to imagine that you have a vertical line and that you could even use your pencil and you're moving it across the function, moving it from left to right across the relation. If the graphed relation crosses your pencil, your vertical line, in only one place at a time, then yes, it is a function. And that's true for A here. Yes, that would be a function. But now B, so imagine I had my vertical line. If my vertical line were going like right here, okay, it actually crosses the relation in two places at the same time, so this would not be considered a function. A function rule is an equation that represents the output value in terms of the input value. So it tells you what y is in terms of x. The function rule can be written in function notation as follows. So you're familiar with something like y equals 3x plus 2, where your input is going to be your x value, and then you multiply that x by 3 and you add 2 to it, and then you get your output of y. Function notation uses this notation here, which you may have seen before, and it's read as f of x. So here we would say f of x is equal to 3x plus 2. It's not f times x, it's not fx, it's f of x, the function in terms of the variable x. Now, if I want to say that x is equal to 1, I would put 1 in here, and so I can say f of 1 is equal to 3 times 1, which is what I put in there for x, plus 2. So f of 1 is the output when 1 is the input. And then I would evaluate that and do 3 times 1, which is 3, plus 2 would give me 5. So I could say f of 1 is equal to 5. When x is 1, y is 5. The independent variable x is the input of the function, and the dependent variable y is the output of the function. So let's take a look at a couple examples here. Evaluate each function for the given value. So here we have f of x is equal to negative 3x plus 2, and I need to find f of negative 4. So that means that I'm going to take my function for f of x, and in place of x, I'm going to put in negative 4. So that gives me negative 3 times negative 4 plus 2. Now I just use order of operations on that. Negative 3 times negative 4 is 12, plus 2 is equal to 14. So I could write f of negative 4 is equal to 14, and written as an ordered pair, it would look like negative 4, comma, 14. Functions don't need to be named f. You can use whatever letter you want in front. So here we have g of x is equal to x squared plus 2x, and I need to find g of negative 4a. So I want g of negative 4a. So I'm going to plug in negative 4a for x. So that's going to be negative 4a squared. Notice it's going to be the whole thing squared, so I use parentheses, plus 2 times negative 4a. So negative 4a squared gives me a positive 16a squared, and 2 times negative 4a gives me negative 8a. So g of negative 4a is equal to 16a squared minus 8a. And let's take a look at an example that involves a graph here. The function y equals f of x, which is just some random function, is graphed at right. So I want to know, what is f of negative 1? Remember that this means that x is going to be equal to negative 1. So in other words, what is y when x is negative 1? Well, right here, it looks like I'm counting by halves here. Right here, x is negative 1. So we'll go up to the function. That gives me this point right here. So f of negative 1, my y value there is going to be 2. Now it says, what is f of x when x is equal to negative 3? Well, when x is negative 3, my y value right here is going to be 0. So f of negative 3 is 0. And my last one here says, what is x when f of x is 4? So when f of x, or my y value, is 4, my x is going to be this point here, which is negative 2. So x is equal to negative 2 when f of x is 4. And that would be represented by this point right here. Often a function can model a real-world situation. It's important to identify the independent and the dependent variable in the situation. The relation can often be described by a phrase such as, distance is a function of time. This means that the distance traveled depends on how much time has passed. So let's take a look at an example and see if we can identify those. A pizza costs $14 and the flat delivery fee is $1.50. Write a function rule to model the total cost of the number of pizzas delivered. So what we want to say here is that the total cost is going to be dependent on the number of pizzas that you order. Or the total cost is a function of the number of pizzas. So I'm going to, instead of using, I could use f of x notation, but I'm going to say let p equal the number of pizzas, and c is going to be the total cost. Oops. Then I can write my function as c of p. My cost is dependent on the number of pizzas. Well, each pizza costs $14, so that's going to be 14p. And no matter how many pizzas I order, there's going to be a $1.50 delivery fee. So that would be my function rule. C of p is equal to 14p plus 1.5. Now I want to evaluate this function for 5 pizzas. In other words, what is c of 5? So that's going to be 14 times 5 plus 150, or 70 plus 1.5. Remembering this is money, $71.50 for 5 pizzas. So in this video, we kind of took a look at what a function was, how we determine something is a function either by looking at how it's represented as a table of values, also how to determine if a relation is a function, if it's a graph, how to deal with function notation, and how to write a function rule given a real life situation.